Yes, so welcome to everybody. Good afternoon. Welcome to the people online. So it's a great pleasure this afternoon to have Shiraz Minwalla from the Tata Institute, and he will give us a review on lessons from the large N solution to matter Chern-Simons theories. Thanks. Please, Shiraz.
Thank you very much. Thank you, Francesco, for the invitation. I would have loved to be with you guys in Florence, and it's just proved too difficult. Next time. Okay. So my talk is titled Lessons from the Large N Solution to Matter Chern-Simons Theories, and is based on 10 years of work by many people, some including myself. So I've given a lot of references here. The talk itself will have very few references, or maybe no references, just to unclutter everything else. Okay, so let me start with an introduction. Chern-Simons theories coupled to dynamical matter fields are of interest for several reasons. The first one is just one of Wilsonian genericity. If you've got a three-dimensional field theory and it has gauge fields and it does not preserve parity, or in some situations even when it does preserve parity, and you flow this theory down to the infrared, you should expect the gauge dynamics to be governed by a Chern-Simons term. Just because the Chern-Simons Lagrangian is one derivative compared to the Maxwell-Lagrangian or the Yang-Mills-Lagrangian, which is two derivatives. So the Chern-Simons terms are just the most relevant terms in the infrared, and so we'll generically govern gauge dynamics. And then in appropriate situations, these Chern-Simons terms will be coupled to matter fields. So Chern-Simons matter theories should represent reasonably generic low energy behavior of field theories in 3 dimensions, at least when they violate certain discrete symmetries. For this reason, one should be interested in understanding Chern-Simons matter dynamics, just because it's sort of like the generic behavior of a non-trivial gauge matter system in 3 dimensions. There's another reason to be interested in these theories is that the object that plays the role of the gauge coupling, the same role that G-squared Yang-Mills plays in Yang-Mills theories, which is 1 over k, is a discrete parameter, and so does not run continuously under the renormalization group. This means it's more or less trivial to satisfy the beta function equals 0 condition for the gauge coupling of a Chern-Simons Chern-Simons self-coupled gauge theory. And for this reason, it's particularly easy to use Chern-Simons theories coupled to matter fields to make conformal dynamics, to generate conformal dynamics, much easier than, for instance, the analogous problem for Yang-Mills coupled gauge dynamics in 4 dimensions, where you've got one additional beta function equation to take care of, and it's typically hard to get that thing to be conformally invariant unless you run through some hoops. Third, Chern-Simons matter theories describe dynamics that is different from dynamics that many of us are familiar with. For instance, some of the particles that these theories describe are anionic particles. They have non-half integer spins. You know, we used to particles all having spin 0, half, 1, so on. In 3 dimensions, that doesn't have to be the case. And Chern-Simons matter theories are examples of theories in where it's not the case. Okay, so these theories, because they have non-half integer spins, they behave in some different ways, show some different dynamics than is more familiarly encountered. And we'll see some of this as we go along in the talk. In particular, we'll see that scattering in Chern-Simons matter theories has properties that are very unusual. In particular, the crossing symmetry properties of these scattering matrices in Chern-Simons matter theories get modified. Fourth, like some of their Yang-Mills counterparts, matter Chern-Simons theories have, in the large N limit, have gravitational dual, ranging from the usual, for instance, like ABJM theories, which have a usual, which means extremely interesting, rich supergravity dual description, to the more weird. Many of the theories we will study in today's talk have Vasiliev type dual descriptions. Okay, so Chern-Simons-matter theories play into the study of ADS CFT in an interesting way. That's another reason to be interested. One of the main reasons to be interested in the theories that I'm going to be studying is the following. The detailed study of these theories has given fabulous evidence that the theories I study enjoy a sort of strong weak coupling duality, which relates bosons on one side to fermions on the other. Okay, this novel and interesting duality in a non-supersymmetric theory is another reason to be interested in these theories. And finally, and from the point of view of my talk, perhaps the most important reason to be interested in these theories is that, you know, not only are all these things true or sort of conjectured to be true, but many of them can be seen to be true because these theories have two interesting corners in which they are exactly solvable or effectively solvable. And so many things can be, you know, computed in these theories without conjecture. The two limits in which these theories are, you know, completely solvable, well, one of them is a familiar old one. This is a story that goes back 30 years. In the limit where you take all the masses of all your matter fields and take them to infinity, then your Chern-Simons-matter theory reduces to a pure Chern-Simons theory. And we've known for over 30 years that pure Chern-Simons theories are exactly solvable and have been exactly solved by Witten and then others, leading to, you know, in a very beautiful way, leading to beautiful mathematics, beautiful connections with other branches of physics. This will play an important role in what I say. But the main point of this talk is that there is a second limit in which these Chern-Simons-matter theories are also exactly solvable. It's a small little corner in the space of all possible Chern-Simons theories. The limit is one in which you take these Chern-Simons-matter theories, you couple them to matter in the fundamental representation. You know, so they matter is like column vectors of UN or SUN, and then you work in the 't Hooft large end limit. Turns out, as I'll explain in this as we go along, these Chern-Simons-matter theories are effectively solvable in this limit as well. Now, this is very important because you see, pure Chern-Simons theories are solvable, but they're topological, as I will be explaining in more detail very soon. These Chern-Simons-matter theories in this fundamental large end limit are solvable without losing all, you know, some of the richness of ordinary quantum field theory. So the solvability of these theories in two limits will, you know, is sort of the reason I'm giving this talk, especially in the last one. Okay, so I've structured my talk as follows. First, we will have a maybe 10-minute review of pure Chern-Simons theories, where I'll review the results that I will need later in the talk. Then I will tell you a little bit about the Chern-Simons-matter theories we'll be studying and give you some general sort of semi-quantitative analysis about these theories, understanding something semi-quantitatively. And then the last, well, more than the last hour, so maybe the last 70 or 80 minutes of the talk will be about detailed quantitative information we can get from the study of these theories in the large and limit and what we learn from all of this. Of course, please feel free to interrupt me at any point. Okay, so let me start with the review of pure Chern-Simons theories. Let's start with this study of SUN level K Chern-Simons theories. So SUN level K Chern-Simons theories are defined by a three-dimensional action, and I've written this action down for you. I'm working in Euclidean space. Okay, this action has SUN valued gauge fields. So Y mu is an SUN, so a Hermitian traceless matrix, and K is at the moment just some number. This action plus a particular regularization scheme defines the path integral of Chern-Simons theory. This action is when I use this action where with the variable that I call K, I will always behind this term I will always regulate any divergences that appear in this theory by adding an infinitesimal Yang-Mills term in the Lagrangian. That turns out to regulate all divergences in a very nice way. For calculation purposes, it's often convenient to use another regulator, a regulator where you take the theory and you use dimensional regularization. And the theory with this action with the Yang-Mills regulator has been demonstrated to be the same as the theory the same theory with a slightly different action with the dimensional regulator. And the slightly different action just differs by a shift in this K. So K goes to kappa in this dimensionally regulated action, where kappa is K plus N, appropriately said. So mod of kappa is mod K plus mod N, and the sign of kappa is the same as the sign of K. Okay. Now, most of you are very familiar with this action, but just for those who may not have seen it so much before, the first thing that occurs to you when you look at this action is that it doesn't look gauge invariant, because it's not an action built only out of field strengths. The gauge field y mu itself appears in the action. Okay. Now this appearance is misleading. One can demonstrate that the transformation of y mu under small gauge transformations is a total derivative. Under large gauge transformations is also a total derivative, but total derivatives is sort of dangerous under large gauge transformations. And one can demonstrate, as most of you know, that this action describes a gauge invariant path integral, provided k and therefore kappa are integers. That's what sets the normalization of this theory. So this is the first thing we see about these theories. The effective value of the coupling constant, 1 by g squared Yang-Mills in these theories, the analog of 1 by g squared Yang-Mills, is the inverse of an integer. It's discrete, and it's what I promised you at the beginning of the talk. The second thing that you might notice if you look at this action is that the metric does not appear in the action anywhere. You know, I've really written it literally as d3x without a square root g d3x. Okay. Nonetheless, this is generally covariant action. One way of thinking of that is there's a square root g here, but there's the generally covariant epsilon has a square root 1 over square root g, and those two cancel. Okay, so because this thing is generally covariant without the appearance of a metric, this describes, at least classically, a topological field theory. And it turns out, though there are some bells and whistles, this classical feature is inherited by the quantum theory. So Chern-Simons theory defines a topological field theory. Now, the next thing that you can easily see is if you take this action and you vary it with respect to y mu, and you compute the equations of motion that follow from this action, you find that the equation of motion is this field strength as a matrix. The matrix valued field strength is 0. Now, that immediately tells you that there are no local degrees of freedom in this theory, because locally, every on-shell gauge configuration is pure gauge. So, in fact, all on-shell gauge configurations can be thought of as maps from the manifold on which you're working into the gauge group, and single-valued maps. You know, two such maps that differ by single-valued gauge transformations are to be thought of as the same as usual. Those are just gauge equivalent. So the space of on-shell solutions, the phase space of our theory, is very limited one. Everything has, global effects are everything in this theory. And I'm going to give you one example of how that works. So consider, for instance, SUN-K, Chern-Simons theory, on the manifold sigma g times S1, where sigma g is just some genus G Riemann surface, and S1 is a circle. Now consider this, doing the path integral of this Chern-Simons theory, not just on this manifold, but not just simply on the manifold, but in the presence of Wilson line insertions. These Wilson lines, that the ones I'm considering, are inserted at points on the genus G Riemann surface. They stay at the same point, but they wind around the circle. Okay. Now you could ask, well, suppose I take this path integral and I cut it at some constant time slice. That cutting should describe some Hilbert space. You could ask what that Hilbert space is. Well, the phase space that I described to you above can easily be seen to be the space of all maps from this punctured Riemann surface into the group. And these maps are, two different maps are equivalent if they are, gauge equivalent up to single valued gauge transformations. And these maps have the property that the group element has to wind around each of the punctures. And the winding is specified up to some equivalence class, up to similarity transformed by the gauge group. And the precise nature of that winding depends on the representation of the Wilson loop that was going through that puncture. Okay, so quantization of this, producing this Hilbert space, is quantizing this phase space, and this phase space was very, amazingly beautifully quantized by Witten in his famous Jones polynomial paper, where he realized that the quantization of this phase space gives you the space of conformal blocks of SUN level K Wessel-Witten theory with local primary operators, holomorphic primary operators located at the points of insertion, where the Wilson loops pass by. Now, since our theory is topological, all states in this theory have zero energy. So when we compute the partition function, we're just computing the dimension of this Hilbert space. So the partition function of Chern-Simons theory on sigma g times S1 is simply the number of the dimension of the space of conformal blocks of SUN Wessel-Witten theory with these insertions at these points. Okay, and now to be totally pedantically precise, because I'm going to need that later in my talk, we can compute this path integral using the Verlinde formula. Recall that the Verlinde formula is this famous formula in conformal field theory that tells you what the dimensionality of the space of a certain set of conformal blocks is. So in particular, using Verlinde's formula is often presented in an abstract looking form involving S matrices and so on. But if you take the explicit expressions of these S matrices for SUN theory and you process it, you can show that this formula amounts to the following. What one is supposed to do is to evaluate the characters of all the representations one has on a bunch of different UN matrices. Now, the UN matrices are matrices whose eigenvalues are W1 to Wn. Because they are eigenvalues of a UN matrix, all these W's have modulus 1. Because they're eigenvalues of an SUN matrix, the product of WI's is 1. But the special thing about this Chern-Simons theory is that, you don't evaluate on all such eigenvalues. You evaluate this thing only on some discretized set. And the discretized set is the set that obeys the following. The ratio of Wi by Wj to the power kappa for any two different eigenvalues in your set, in your unitary matrix, that has to be 1. So Wi to the power kappa, all eigenvalues amount to the same when raised to the power kappa. Also, no two eigenvalues are allowed to be equal. Okay. Now, these four conditions, the conditions that we've got n eigenvalues, obeying these four conditions, that it's a phase, that the product of eigenvalues is 1, that all of the eigenvalues amount to the same thing when you raise them to the kappa power, and no two eigenvalues are allowed to be equal, defines a set of equations. This set of equations has a finite number of solutions. Actually, it's easy to count. It's possible to count the number of solutions. And what you're supposed to do is to take, for each one of these solutions, you're supposed to evaluate the character, weight by this sort of measure factor, and then sum over all solutions, and then weighted by a normalization factor. That object there, because of has been shown by Verlinde, and there are other methods to see this as well, to be the number of singlets, that is the dimensionality of the space of conformal blocks that we were interested in, threaded by these primary operators. Okay, this formula actually only holds when the representations in question are so-called integrable representations. If you don't know what that is, I'll tell you about that in a bit. Well, I've said it here. It's only holds when the dimensional when no row in the Young tableau of the corresponding to the representation has a length greater than k. Okay, so this is an example of an exact result in Chern-Simons theories. You want to know the path integral of this matter Chern-Simons theories with these insertions of Wilson lines. Here you go. This is the answer. Okay, we come back to this formula as we move along. Now, 2 minutes more about pure Chern-Simons theory before we get to the real topic of our this lecture. I'm going to need in this lecture also to look at more than SUN K Chern-Simons theories, but also to look at UN KK prime Chern-Simons theories, UN Chern-Simons theories. Now, unlike their SUN counterparts, UN Chern-Simons theories, where am I? Unlike the SUN counterparts, UN Chern-Simons theories are not characterized by a single level, but by two levels. Roughly, you can think of these as the levels for the SUN part and the level for the UN part. Okay. When we talk about the level K prime for the UN part, I always work in a normalization such that under this, the gauge fields that we're working with, fundamental fields carry charge 1. Now, had UN really been SUN times UN, both K and K prime would just have been integers. But SUN is not, UN is not SUN times UN, and that gives you some sort of connection between these two levels in order for the thing to be consistent. When you work it out, you find that the connection is that K prime, the level for the UN theory, has to be kappa or K, well, let's say kappa for the SUN theory, plus an integer, Q is an integer, positive and negative, times N. This is a consistency condition that comes out when you study these things. Okay. Nonetheless, even though it's it's a rarefied integer, there are two integers that label your UN Chern-Simons series. These are two integers can be thought of as K and K prime or K and Q. Now, in this talk, we will be particularly interested in two special values of Q. We will be interested in Q equals 0, which I will sometimes call the type 1 theory. At this point, when Q is 0, K prime is just kappa, as you can see from here. Or we will also be interested sometimes in Q is equal to -1, at which point K prime is equal to K. Now, I should say that some of these formulas, I have written some of these formulas assuming all quantities are positive. Like this formula really should have had a sign of K inserted here. I've not put that, I apologize. So unless otherwise stated, you should assume that K and K prime are both positive integers for the formulas as I've written them to be correct. Okay. Now, once again, the partition function of the UN KK prime theory on the genus G manifold times S1 in the presence of Wilson lines is given by the space of UN KK prime Wesson-Witten blocks. Once again, there's a Valinde formula to compute that. Once again, this formula can be processed, and you get a formula that's sort of similar to that of the SUN theory. Once again, you've got a sum over, you've got a something, characters, and some measure factor over the set of solutions of some equations. Once again, you can argue and argue that these equations have a finite number of solutions. You can count them, and this gives you the final answer for the partition function of UN KK prime theories on sigma G times S1, or which is the dimensionality of conformal blocks with these primary operator insertions.
Sorry,
yes.
Can you repeat it? Chi is a character of what? I didn't
I'm sorry. Yes. Chi. Okay, good. So let's start here in the SUN things. Okay, you remember what we had was SUN theory with Wilson lines going through, going around the S1 at various points on the genus G manifold. Now these Wilson lines were in some characters, in some representations. Okay, so let's say the first Wilson line was in representation R1, the second Wilson line was in representation R2, and so on. R1, R2 are some representations of SUN. Chi is simply the character of SUN, just simple SUN character, evaluated on a particular unitary matrix. That unitary matrix is the matrix whose eigenvalues are W1, W2, W3, up to Wn. Is this clear?
Yes, thank you.
Yes, I'm sorry if I'm going, please do stop me if something's not clear or otherwise. Okay, any other questions or comments?
No.
Okay, excellent. Yeah, so this formula that I've written here, is simple enough, but it simplifies even more in the case Q equals 0. In the case Q equals 0, this equation here simply becomes all of the eigenvalues to the kappa power have to be -1 to the power n plus 1. Okay, I put these -1 to the power n plus 1s in red because a naive path integral derivation of this formula, I'm sparing you the details, doesn't produce this, but the Valinde formula does, and we've got many checks that it's correct. But it's an interesting factor that doesn't come out of path integrals if you're naive, at least. Okay. So anyway, it's the correct form. So in this case, what we're supposed to do to evaluate the number of the partition function and the number of singlets, number of conformal blocks, is to perform this even simpler looking sum. Here, all of the, so for instance, suppose n was odd, when all of the eigenvalues are kappath roots of unity. If n is even, all of the eigenvalues are kappath roots of -1. They all have to be distinct. And then we have to sum over all possible collections. So suppose n was odd, you have to sum over all of the kappa Cn in equivalent collections of kappath roots of unity. Okay. So this formula becomes really very simple. This is the formula that tells you what the number of conformal blocks is in the type 1 theory. Okay. Now, something, and I've now specialized this formula to working on a particular genus G manifold, namely the sphere. Now, if you look at this formula, it might remind you of something. You see, this factor here is these Wi's. You should think of as the the eigenvalues of the holonomy matrix if you were doing a path integral. This factor here, therefore, is a van der Waals factor. Okay, this factor is a van der Waals factor, and in the large end, so you can look at this and see that this looks very much like a particular discretization of the Weil integral formula that counts the number of singlets just in group theory. So the Weil integral formula would ask you to evaluate products of characters and integrate over Haar measure. But integration over Haar measure is simply integral over the phases, multiplying by this van der Waals factor. The fact that this is a sum, a very particular discretization, not the integral, tells you it's a deformation of the Weil integral formula for the number of classical singlets of classical group theory. But the fact that it is a discretization tells you it's sort of not too dissimilar an object. And in particular, this similarity becomes clearest in the large n limit. If we work in the Toth limit where n goes to infinity and k goes to infinity with n by kappa held fixed, then the size of this discretization, you say you're discretizing over all possible kappath roots of unity, the difference between one and the next is very small. So this thing really becomes sort of like a discretization, you know, becomes like an integral. However, there is a catch. And the catch is that that integral is not over all eigenvalue distributions of this holonomy matrix, but only those eigenvalue distributions whose density of eigenvalues is not larger than 2 pi n by kappa, which is 2 pi by lambda. And this you can see very easily by just looking at a local patch and asking all slots, all possible kappath roots of unity to be filled. And then define the density, compute the density of eigenvalues there, using the fact that eigenvalue densities are normalized with a factor of n. And you will see that that comes out here. Okay. So what we've got here in the large n limit is actually the Weil integral formula with a constraint. We don't integrate over all unitary matrices. We integrate with the same measure as Weil would have, but not over all unitary matrices, only those that obey the condition that the eigenvalue density of our holonomy matrix is everywhere less than 2 pi, point-wise less than 2 pi by lambda. Okay? So in the large n limit, this is a particular limit, a particular cutoff, sort of cutting off a part of the space of the Weil integral formula that gives you, that computes singlets in classical group theory. Okay, so I've said what I just said in words, I said that in equations. This number of singlets goes over to something that looks very much like the Weil integral formula. However, this with a modified measure, and this modified measure is the Haar measure, but restricting your set of unitary matrices that you integrate over to be those whose eigenvalue density function point-wise does not exceed 1 by 2 pi mod lambda. Okay, then the last thing I want to say about pure Chern-Simons theories is this. Pure Chern-Simons theories enjoy invariance under a remarkable strong weak coupling duality called level rank duality. Okay, There's actually one more that will play no role in my talk, but the ones I'm going to be talking about are the following. There's a duality between type 1 and type 1 theory. That is a duality between the UNK kappa theory and the U mod kappa epsilon n epsilon mod kappa theory, where epsilon has the sign of minus k. There's also a duality between the SUN theory and the type 2 theory, okay, which I've listed out for you. These two level rank dualities will play an important role in what I'll be saying in this talk. Now, in what sense are theories, what sense are level rank dual Chern-Simons theories the same? Well, the first sense is that if you've got some manifold and you compute the partition function of the Chern-Simons series of these two on the same manifold, these two would give you the same answer. But that is upgraded also to the partition function in the presence of Wilson lines. When you do that, however, there's a non-trivial map between representations of Wilson lines. You take Wilson lines in one theory and the Wilson lines in the level line dual theory. They're not in the same representation. Indeed, there's no sense in which they could be in the same. Well, they couldn't be in the same representation because they're different UN groups. But the map between representations is known and understood, and it's sort of complicated in general. But for simple representations, it's very simple. In particular, for the fundamental maps to the fundamental, and the M index symmetric representation where M is less than K maps to the M index anti-symmetric representation where M of course is less than N. And then there's some plus ones and minus ones depending on whether you're UN or SUN. Okay, so the basic point is that symmetric maps to anti-symmetric. And this is in a way our first hint that this level rank duality here was born to be upgraded to a Bose-Fermi duality. And we'll see how that works as we go. Okay, that's all I want to say about pure Chern-Simons theories. I'm sorry to have taken so much time. Any questions or comments about this before we proceed to adding matter to these things?
Maybe I can ask a question. So regarding this sum that becomes an integral, but becomes an integral with a constraint.
Yes.
So you also have the Vandermonde. So is the Vandermonde somehow taking care of the constraint in the sense that one might think that maybe if you try to clamp the eigenvalues,
yes,
the Vandermonde kills that contribution even without the constraint.
Good. You might think that, but that's not the case. For instance, suppose you took just a pure Yang-Mills theory and you looked at its partition function modulo the singlet condition. Okay, that gives you that evaluates in the end to an integral over the unitary matrix, which is the holonomies. And in the large temperature or large volume limit, that holonomy distribution function is dominated by the delta function. That delta function has height which exceeds any finite number you get, and in particular is larger than 2 pi by lambda. Okay, so you see, as you said, Francesco, the Vandermonde tries to push things apart, but it's a smooth pushing things apart. There's a potential that you push harder on it, it squeezes more. And there's no limit to how much you can squeeze. Whereas here you get a hard cutoff. No matter how hard you push, you cannot squeeze the eigenvalue density function to be locally larger than 2 pi by lambda. And this makes almost no difference at low volumes or low temperatures, but makes a big difference in theory at high temperatures or high volumes, when the pushing is very, very hard. Does this answer your question?
Yes, thank you. We have a question.
Okay. Any other questions or comments?
Yeah, sorry. So is this related to the fact that Chern-Simons is deconfined, while if you take Yang-Mills is confined, so the density of eigenvalues is a bit different?
No, it's not related to that. So suppose you took just a Yang-Mills theory on a sphere and you made the size of the sphere very small compared to lambda QCD. Then Yang-Mills theory is also deconfined. And you get a very similar formula like this, but with the actual y initial. So this is a different thing. It comes from the fact that there are non-trivial topological configurations in the Chern-Simons theory, these flux sectors, and the sum over flux in the path integral formulation discretizes the eigenvalues. That's the path integral way of seeing this happen. So it's a very three-dimensional phenomenon and very much depends on the Chern-Simons Lagrangian, but it's not about confinement.
Okay, thanks.
Okay. Excellent. Any other questions about this? Excellent. Fine. So now that we're all experts on pure Chern-Simons theory, we can congratulate ourselves, but also have the sneaking suspicion that we haven't done what we really should be doing. Because, pure Chern-Simons theory, as I explained to you, is a topological field theory. It's a theory without local degrees of freedom. It's not really a quantum field theory. And if we feel our job is to understand quantum field theories, it feels almost like we've cheated, right, by studying Chern-Simons, pure Chern-Simons theory. So let's uncheat. Let's take this pure Chern-Simons theory and couple matter to it. Now, the gauge fields have no local degrees of freedom. That doesn't change. But the matter fields do have local degrees of freedom. So now we're looking at a real quantum field theory. So now let's start trying to study this. Okay, so I'm going to be looking at two particular classes of theories. Two particular pairs of classes of theories. The first one is simply a theory that would have been free fermions with a mass had it not been minimally coupled to a Chern-Simons gauge field. This I call the regular fermion theory. Regular because it would just be an ordinary free fermion theory had it not been for the Chern-Simons. The second one is a theory that is written in a form that you may not be completely familiar with. But if you think about it a little bit, at least in the large n limit, this theory, had it not been gauged with respect to Chern-Simons theory, would have been the Wilson-Fisher theory with a mass deformation. Three-dimensional UN flavor Wilson-Fisher theory, and then gauged with respect to Chern-Simons theory. Okay. This theory has fermions, this theory has bosons. Okay, and I'll be studying this thing I call the regular fermion theory. This I call the critical boson theory. This pair of theories, it's in some sense the simplest Chern-Simons-matter theory to study. I'll be studying it in some detail. Okay, if you want to be very fine, to really specify what you're doing, you need to specify the regulation scheme and so on. But I won't bother you with such details in this talk. Now there is a second pair of theories that I'll be studying. Okay, and the second pair of theories goes as follows. The first one, which I call the regular boson theory, is just a theory of free bosons with a mass, but then also with a phi to the 4 potential and a phi to the 6 potential. This is the theory that would have been had it not been gauged with the Chern-Simons with a Chern-Simons coupled gauge field. Okay. This guy, on the other hand, the fermionic guy, is slightly more strange. What we do, I forgot to define J0. Sorry, J0 is psi bar psi divided by 4 pi. What we do is take this free boson theory, and then we add a Lagrange multiplier to it. Psi bar psi times divide by 4 pi times zeta. That's this, and then we add a potential for zeta. The zeta is some new scalar field in the problem. Okay, and this pair of theories I'm going to call the regular boson and critical fermion theories. Okay, now it's very easy to argue that at least in the large n limit, but unless something drastic happens more generally, that these are well-defined field theories. It's much less easy to argue the same for these two theories, and there are two issues that arise. One is that this phi field here is a floppy field. So once we start doing path integrals, it could be that it develops a runaway potential and the theory doesn't make sense. The second issue, which is in a way even more basic, is that this Lagrangian, because this has a marginal operator, large n marginal operator here, will run. And indeed it does run, and one can compute its running by computing its beta function. Okay, and for the theory to be well defined, it's got the beta function has to have reasonable behavior. It has to have the place where it stops, the running stops, and then you can think of these theories that we define as a flow away from these conformal theories. Okay, both these issues have been studied and in detail in the large n limit, and at least in some range of parameters, one has been able to argue with confidence that neither of these issues is a problem. So these theories, at least in the large n limit, sometimes despite appearances and despite some people's misgivings, exist, they make sense, well-defined theories. Okay, they're less simple than these theories. And we'll come back to them in a minute. Okay, now I've studied these theories in pairs because, as many of you know, these pairs of theories are conjectured to be dual to each other. So this guy is conjectured to be dual to this guy. This fermionic theory is conjectured to be dual to this bosonic theory if the Chern-Simons theories are related as follows. Now, I should say one word about notation. When I give you the, you see, when I tell you the level of a Chern-Simons theory coupled to bosons, well, that's pretty unambiguous. But when I give you the level of the Chern-Simons theory coupled to fermions, okay, what I mean by this is the following. I take the theory, imagine if the theory does not have a mass, I give a mass to the fermions. If it has a mass of the wrong size, I change the mass for the fermions. I change it so that the theory has a mass which has the same sign as K. Then I integrate out the fermions. And K then is the final level that I get at low energies after I finish this process. Okay, so some people would write K minus half here. But what they mean by that really is that if you took this fermion and gave it a mass with the same sign as K, then the final low energy effective action would have a level K. So this is what I mean by K. Okay, so and then some notation which we've already seen in some, just to say it again, kappa is the shifted level for the bosons and similarly for the fermions. Lambda is n divided by kappa. And the two pairs of bosonic and fermionic theories have been conjectured to be dual. I give you all the formulas for the critical boson and regular fermion theories. There are similar formulas for the other parameters for the other two theories. I haven't bothered to write it down here. Under basically level rank duality, K and N are interchanged up to signs. And then there's a known relationship between the masses of the two theories. For the critical boson and for the regular boson and critical fermion theories, there are more such known relations between all the massive parameters of the theories and also the marginal couplings. Okay, and you can rewrite these duality maps in terms of kappa or in terms of lambda. So, okay, these duality maps are believed to be exact. This is only known at large n because you can do calculations. Check it and may be corrected by 1 over n corrections. Okay, now this conjectured duality, I'm just introducing it to you here. I'll tell you much more about this duality. But this conjectured duality is the reason I consider these two pairs of theories together and these two pairs of theories together. Okay, fine. So now before I get to really quantitative large n stuff, okay, it's useful first to just take a look at these theories and see what you can roughly say about them. Okay, so let's first start with the simpler pair of theories. Okay, the critical boson and the regular fermion theories. And for the rough analysis, I'll only look at these theories. These theories, one can argue easily at large n and perhaps with some plausibility at finite n and k, are conformal when we take the two masses in the dimensional regularization scheme and set them to 0. Now, that's great. So we produce conformal dynamics for these two theories. However, for what I want to say, it's a bit of a pain because I want to study particle-like excitations in these theories in my rough qualitative analysis section. And conformal theories don't have infinitely long-lived particles. Okay, so this motivates the study of massive deformations of these conformal points. Now, what are the massive deformations of these conformal points? Well, they're just deformations by this mass, right? We tune the mass to 0 to get the conformal dynamics, but we untune the mass away from 0 and we get into massive phases. Okay, so there's only one relevant deformation in these theories. Both these theories, it's a mass term. And the mass is real. So there are, up to rescaling, there are basically two different deformations. You can deform with a positive mass, you can deform with a negative mass. You'll flow down to the same phase. After that, it's just scaling. Okay, so now we're going to quickly see what happens. I mean, what would you expect to happen naively if you took the bosonic theory and deformed with a positive mass square in some sense, in the bosonic side, though MB Cree is like the mass square, or what you normally call the mass square. Okay, so positive MB Cree. You probably don't remember what MB Cree is, but it's a positive mass. Okay, now, if you take a theory of, spins and you deform it with positive mass, then all the spinor excitation, these spin waves become massive, right? So positive mass deformation takes you to basically what you think of in a spin system as being a paramagnetic phase. Okay, the elementary excitations, sort of like spin waves created by the boson Phi, have now become massive. Very simple physics. Okay, now this is not quite a spin system, it's gauged, but that doesn't really matter very much for what I said. However, if you take the same system and you deform it with a negative mass square, then in a spin system, what you would get is spontaneous symmetry breaking. You'd go into the ferromagnetic phase. Okay. However, here, the fact that we're dealing with a gauge theory makes a big difference. Because you see, spontaneous symmetry breaking never happens with gauge theories. What you get is instead is the Higgs mechanism. And you can work this out in detail. In large and limits, we worked out with great quantitative detail. And you find that that's the case. You get, if you turn on a negative mass square, you trigger the Higgs mechanism. SUNB is broken down to SUNB minus 1, and the degrees of freedom that would have been in the scalar field are eaten up by the Higgs mechanism and go into vector bosons. Okay, so the theory becomes a theory of massive vector bosons. This is which I call W bosons, which are the fundamental of SUNB minus 1 by the Higgs mechanism. Okay, so these are the two. This is roughly how you should think of these bosonic theories. There's two different phases separated by phase transition. It's a second order phase transition. Dynamics is conformal there. One phase, you've got massive fields where the massive fields are scalar-like, created by Phi. The second phase, you've also got massive fields where the massive fields are vector-like, created by W. So much for the bosons. What about the fermions? Well, for the fermions, when you turn on the fermionic mass, you turn on M either positive or negative. Qualitatively, classically, it doesn't make much difference. There are some small differences. But classically, it doesn't seem to make much difference. So what you get is a theory of massive fermions, either with positive mass or negative mass. However, if you look a little more closely, you see that there are differences that you can see. So, for instance, if I turn on the fermions with positive mass, sort of by definition, what I mean by this K at these levels, since I'm dealing with type 2 theory, by definition, I would get the level of the low energy Chern-Simons theory would be K, K. But if you turn it on with, and when I say positive mass, I mean mass of the same sign as K. Positive mass of K is positive. On the other hand, if you turn on a negative mass in the convention where K is positive, you find that the low energy Chern-Simons theory becomes reduced by 1. K goes to K minus 1. Okay, so there's a difference between the two low energy theories, depending on whether you've turned on positive or negative fermionic mass. Also, remember that the low energy theories on the bosonic side were also different, because the Chern-Simons theory either had SUNB or SUNB minus 1 because of the Higgs mechanism. And you can very nicely see that under the level rank duality of pure Chern-Simons theories, this guy is dual to this guy, whereas this guy is dual to this guy. Because K has been reduced by 1, N has been reduced by 1. Okay? So, roughly speaking, these two phases, on the fermionic side, it looks like nothing particularly dramatic is happening when you turn on a positive or negative mass. The bosonic side, it looks like it's completely different. You've gone from paramagnetic to ferromagnetic phase. But actually, if you look at it carefully, it looks like it's working. Now, you might be a little unsatisfied about this. And your dissatisfaction may take the following form. You might say, well, on the fermionic side, excitations of both signs are the elementary fermions. Now, how do elementary charged fermionic excitations map to a boson, to a spin 0 excitation on one side and a spin 1 excitation on the other side? Both the fermions have spin, plus or minus half. How can that work? Okay. In particular, that's the simple observation that Phi has spin 0 and W has spin 1, whereas Psi has spin plus minus half, falsify this conjecture duality. The answer is interesting. The answer is it does not, and in fact, it can be used as a test of this duality once you're a little more careful. The point is that these excitations here don't actually have the spin that you think they have. in Chern-Simons theory, when you have a charged field in Chern-Simons theory, it traps flux. And that charge flux system carries some spin. How much spin can be worked out by the Noether procedure? It's a simple semi-classical analysis will tell you how much spin it carries. And turns out that the answer, the final answer is C2R by 2 kappa, where C2R is the quadratic Casimir of the representation. Okay. So the total spin of your excitation is the spin that you see, let's say 0 for phi, plus the spin that you get from Chern-Simons theory. So if spins have to match across excitations on the two sides, what must be true is that the intrinsic spin plus what I call the statistical spin, this Chern-Simons spin, has to match across the two sides. Now, as we've seen, there is this simple formula for the statistical spin. So there's a simple formula for the difference between the statistical spins. And if you put both things in the fundamental representation, okay, you take both things in the fundamental representation, then it's easy to compute what these things are and look at the difference, and you find that it's sine of kb by 2 or minus sine of kf by 2. Okay, so this relationship works, you know, just taking this guy to this side and this guy to this side. This relationship works provided that this difference is equal to that difference. The intrinsic difference is equal to the statistical difference. But this intrinsic spin of a fermionic field is simply given by the formula half of sine of the mass of the fermion. Okay, so putting these together, this works provided the intrinsic bosonic spin is half of sine of the fermionic field minus sine of the fermionic level. Now you see, if the mass and the level have the same sign, so that the dual was, you know, this paramagnetic phase where the excitations were simple spin zero excitations, this is zero, and that matches the intrinsic spin of spin zero excitations. On the other hand, if the mass and K have opposite signs, then up to a sign, this thing is something of modulus 1. And W bosons also have spin 1. And in fact, they have spin 1 with either a plus or a minus sign, and you can check that the sign works out. Okay? So indeed, this apparent paradox between spins, actually, when you resolve it, gives you confidence that this duality might actually work. And, you know, we had to do almost no calculation here, apart from understanding this, which is essentially the formula for the scaling dimension of a primary operator in Western innovative theory. So really, we had to do no calculation. Okay? But it works very nicely. Now, there is an obvious issue with what we discussed in the last few slides. How, you could wonder how, for instance, can the Phi particle map to the Psi particle, for instance, in the unhiggs phase, when there are NB Phis but NF Psis? How could it, you know, okay, you could say everything you want about spins and so on, but, you know, there's this gauge index. There are NB of these Phis and NF of Psis, so how can these excitations really map to each other? Now, this question is an interesting question and it's a subtle one. It's a subtle one because, you know, these guys, these excitations by themselves are really allowed states in the theory only if the theory is formulated on R2, so that the Gauss law doesn't forbid charged excitations. Now, when you formulate a Chern-Simons theory on a space with a boundary, note R2 has a boundary. The boundary is at stri plus and stri minus. When you formulate a Chern-Simons theory in a space with a boundary, you should carefully include also the boundary degrees of freedom. And that nobody has really thought through carefully in the case of matter Chern-Simons theories. Okay, so the safer thing to do is to formulate it on a closed manifold, like an S2. Now, once you formulate this on an S2, Phi and Psi are not allowed excitations by themselves, but are building blocks of allowed excitations. And the building blocks, the final excitation is okay if a sort of gauge invariance condition is maintained. Okay, and I'm going to explain to you in the second quantitative part of this talk that it actually does work out, that the C of Psi particles and the C of Phi particles describe the same Hilbert space, even though there are NB Phis and NF Psis. Okay, but that will come to as we go into the more quantitative part of this talk. Okay, any questions or comments? I'm now entering the more quantitative part of the talk, and maybe we'll take a break, maybe in 5 minutes or so. But any questions or comments before we continue?
Just to be sure, so these particles that we talked about now are the lowest, like the lightest stable excitations in each side.
Yes.
And in principle, there could be bound states. Like
there could be bound states. Yeah, it's a very interesting question. There could be bound states, and in fact, in one situation, we know that's a bound state. I didn't talk about it, but several situations, but one, without doing a calculation. And that situation is when we've got this Higgs phase for the bosons. You see, I talked about these W bosons, but actually, if you work out the Higgs mechanism, there is this charged W boson, but there's also an uncharged Z boson. Okay, and that it's uncharged under the gauge group. There's no elementary. It looks like an elementary particle in the bosonic description. There's no elementary particle in the fermionic description which matches that object. But you can argue from various points of view that this arises as a two-particle fermionic bound state. Yeah, so as you predicted, there are sometimes bound states, and in fact, sometimes something that's a bound state in one description is just classical in the other description, as happens often in duality. It's a very beautiful story, and this part about the Z boson we've not published, but we've worked out in some notes that maybe one day find. Yeah.
Okay, thanks.
Okay, any other questions or comments? Excellent. Fine. So I'll go on for 5 more minutes if that's okay, Francesco, and then stop for the break.
Absolutely.
Yeah. Okay. So now we've done qualitative analysis of these theories, but we want to be more quantitative. How can we do that? Pure Chern-Simons theory you could be quantitative because the theory was so simple. Once you've added matter, it becomes real quantum field theory. What do? Well, it's well known that vector-like large N limits are easy to solve using large N techniques. So if you've got a non-gauge theory, a theory whose degrees of freedom are just columns, and it's like vector-like, that's what I mean by vector-like, columns. Okay, large N limits of such degrees of freedom are typically very easy to solve. Okay. On the other hand, large N limits of theories involving matrix degrees of freedom are typically very difficult to solve. For instance, nobody's managed to solve QCD in the large N limit, or pure Yang-Mills theory in the large N limit in 4 dimensions, though that might get you a Nobel Prize. It would be a fantastic accomplishment, but it's just very hard. Okay. Now, if you're studying gauge theories, you might think you're always out of luck. Because gauge theories always have the gauge fields, and the gauge fields are matrices. So the large N limit may buy you some simplification, but won't make the theory solvable, or so you might think. And that's generically true. However, there are 2 exceptions that I know of this rule. 3 if you count D equals 1, but that's so trivial I'm not counting. Okay. The 2 exceptions are in 2 dimensions where you study Yang-Mills theory, where Toft demonstrated that quarks coupled to large N Yang-Mills theory is a solvable model, famous Toft model, and sort of more or less solved it. The last steps have to be done numerically. Okay. And now there's a new thing that we discovered 10 years ago, which is you take Chern-Simons theory and you couple to vector like a column like matter, and you take the large N limit. That's also solvable. Now the reason that in both cases, the reason that this is solvable is the same, that the matrix-like degrees of freedom were actually more or less empty. There were no propagating gluonic degrees of freedom, either in 2D Yang-Mills or 3D Chern-Simons. And that's why that part could somehow be dealt with, even though it was matrices. Okay. And so in this case, there's one limit of these matter Chern-Simons series, which are also effectively computable. And much of the rest of this talk will be about that limit. It will be about taking matter Chern-Simons theories, working in this large N-Toftian limit, where we take N to infinity, K to infinity, kappa to infinity, with N by kappa held fixed, lambda, the Toft coupling held fixed. Now in this large N limit, many things have been computed. And I'm going to, at least very briefly tell you about all of them. The first thing is about the existence and stability. I told you when we were looking at these more complicated theories, you might wonder about whether they're stable, whether the beta functions have good properties. That has been investigated in detail in the large limit. So quickly tell you about that. Another thing that's been computed is correlation functions of gauge invariant operators at the point where these theories become conformal. 2 and 3 and some 4-point functions, I should have put the word some here, have been computed. And, this is a very impressive check of duality because correlation functions between these theories agree in this large N limit. It can be checked to agree. And then from my point of view, the more interesting structural features, which is what we will get to, are the following. In the large N limit, you can also compute the thermal partition functions of these theories on S2. And that gives you insight into what the Hilbert space of these theories are. I'll spend a lot of time, maybe half an hour describing this. Then you can also compute S matrices of, as the last question asked, these lightest charged particles in these theories. They're stable things, they're as good. They're not gauge invariant, but they're as good asymptotic states as the electron is in QED. You can compute the S matrices of these lightest charged particles. And that helps you understand how both statistics can match Fermi statistics. And it also helps you understand, gives you a surprise about this funny crossing relationship. I'll briefly review that. Then you can generalize the class of theories that you study to include one boson and one fermion and make contact with supersymmetry and a duality that Francesco in his youth, or his even more youthful youth, proposed maybe 12 or maybe 15 years ago now. And finally, you can study these theories in the presence of a magnetic field. I'm not sure I'll be able to tell you about all of these things. It's an ambitious program, but this is what the menu is for the next hour. That's after the break, after a 2-minute break.
Okay, thank you very much.
So I'll be back in a couple of minutes if that's okay.
Do we have some questions before the break?
Please, yes.
Let me just ask a quick question. So
Yes.
all of these that you are going to describe, is it happening just for the fundamental representation or also for some other representation of the matter field?
Only the fundamental representation. The main point of the solvability in the large N limit really is something like this, that the number of degrees of freedom of the fundamental representation is much smaller than n squared. That is somehow very important in being solvable. So everything I say will be in this fundamental limit. Now, you could work you could also solve these theories in another opposite limit, where you take the representation to be very large. In that case, the fact that you have the gauge field would be a small perturbation. These theories would become basically ungauged theories, and the gauge field would become the perturbation of this theory. I think that should also be, it would be like a large flavor limit. That, I'm not sure has been looked at very much. Some people have looked at it a little bit, but it has much less interesting physics, because that really behaves like, almost like you're looking at an ungauged theory and turning on gauging as a perturbation. Whereas here we're looking at the phase in which gauge dynamics sort of dominates everything that's going on. But the really interesting place where you turn on, let's say, adjoint matter or bifundamental matter or symmetric matter, where as many matter degrees of freedom as gauge, that is not solvable using large N techniques. That would be roughly speaking, as hard to solve, at least naively, using large N techniques as QCD would be. Does that answer your question, Francesco?
Yes, thank you.
Yes. Actually, it would be interesting, I think, to look at the other limit a little more than people have looked at it. But somehow I feel that that's a bit trivial. Yeah, but please go on.
Okay, so I think we can take the break, 5 minutes break, and then we will reconvene.
Yeah, and Francesco, I know I'm a little late, but could I have a whole hour after the break? Is that?
Yeah, no, absolutely. I mean, we started 10 minutes late, and now we're also taking the break. So take your time.
Okay, thank you.
It will be great. Thanks.
Thank you.
Okay, I think we can start with the second part. Is that okay, Shiraz?
Perfect.
Yes. Okay. So please.
Okay. So now we're going to try to get a little more quantitative and try to see what large N buys us. So as I said, we're going to try to understand existence and stability, correlators, the nature of the Hilbert space of these theories, statistics and crossing, connections with supersymmetry, and perhaps to magnetic field. So if you remember, when we were looking at these regular boson and critical fermion theories, we had a worry. The worry was that there was a marginal operator, a marginal parameter, x6, that could flow under the renormalization group. Now, one can go some way towards computing the beta function of this parameter. Okay, it's not an entirely trivial computation because it turns out that the beta function vanishes at leading order in large N, and it's non-zero only at first subleading order 1 by N. Nonetheless, one can compute it or compute it to a great degree. I won't go into details here, and demonstrate that the flows for x6 generated by the beta function flows towards the IR take the following structure. There are 3 special at basically any given value of lambda. Some of what I'm saying is not 100% proved. Some is proved, but it sounds very likely to be true. That there are 3 special values of x6 at any given lambda. Okay, and so we're turning all other dimension-full parameters to 0. We're trying to find the conformal dynamics of this theory. We're just looking at the theory deformed with x6 and nothing dimension-full. We're looking at the flows in x6. And there are 3 special values of this x6, which I call 1, 2, and 3. In the limit lambda b goes to 0, 1 and 2 merge with each other. In the limit lambda b goes to its largest value, namely lambda f goes to 0, 2 sort of migrates to be exactly in between 1 and 3. Okay, and the flows are this way. This is an attractive fixed point. These 2 are repulsive fixed points in these directions. Now, all of these theories have 2 additional relevant deformations: the mass and the phi to the 4 operator. So these 2 fixed points define theories with 3 relevant directions, whereas this fixed point here defines a theory with 2 relevant directions. This is the one that will be most interesting to us, as I now explain. So one of our worries is that there were no interesting fixed points in these theories as taken care of by direct computation. However, we had a second one. Our second worry was that the phi field is sort of floppy in these theories. Maybe it could develop a runaway direction in the potential. To test whether this happens or not, all we have to do is to compute the effective action, the quantum effective action for the gauge invariant operator phi bar phi. Okay, nicely enough, it's possible to do this calculation. So we've done it. Classically, the potential for phi bar phi, I remind you, was this. This is what appeared in the Lagrangian for this critical boson theory. Quantum mechanically, when we compute it, we find that for phi bar phi greater than 0, and for phi bar phi less than 0, we get 2 different set of answers. For phi bar phi greater than 0, we get this answer where all that's happened compared to the classical answer is that there's a shift in this phi cube term. And for phi bar phi less than 0, we get another answer where again all that's happened compared to the classical answer is that there's a shift in the phi cube term. Oh, sorry, these things that I call theta 2 and theta 1 here, I've called phi 1 and phi 2 here. This should have been theta 1 and theta 2. Are given by particular constants in terms of the gauge coupling, lambda. Okay, now there are some things that you guys are wondering, some of you are wondering. What do I mean by phi bar phi less than 0? Sigma b was phi bar phi, sorry for the sloppiness in this. What do I mean by phi bar phi less than 0? Isn't phi bar phi positive? But classically, certainly phi bar phi is positive. This potential is defined on the half-line. But quantum mechanically, phi bar phi is an operator defined after you give a subtraction. And that subtracted operator turns out could be either positive or negative. Okay, so phi bar phi now is just an arbitrary real number. So the range for this value phi bar phi goes from minus infinity to infinity. Okay, now you see if either this coefficient goes negative or this coefficient goes positive, okay, then the theory has a potential that's unbounded from below. Okay, so we want to be in a situation where where this guy is positive and this guy is negative. Okay, and so if x6 lies between θ1 and θ2, okay, if x6 lies between θ1 and θ2, that condition is obeyed. So this is the situation in which you have a stable vacuum. Suppose x6 was too small. Let's say x6 was very negative. Then the phi cube term, the coefficient of the phi cube term becomes negative, and that's just the classical instability. You're turning on negative phi cube, negative phi bar phi cube, and phi bar phi, that operator, then can just run to plus infinity. But there's another calculation reveals that there's another potential instability, where if the x6 term is too large, then there is an instability towards running to minus infinity in the operator phi bar phi. It's an odd thing because there's no classical analog of this. But in this range, neither of these is a problem. And so if x6 lies between these two ranges, and this range is non-empty because always there's phi1, which I call θ1, and phi2, which I call θ2. Phi1 is less than phi2. So there are values of x6 where this is nice and stable. Now the question is, what about these fixed point values? They are where they are. Do they lie where this thing is nice and stable? And the net upshot, I've said it in some detail here, but I'm going to hurry because I'm running out of time, is that the net upshot is that this fixed point here, this fixed point 2, for all value of lambda, it appears, wherever we've been able to do the calculation, is always in the stable range. Certainly for small lambda b and large, small lambda b and small lambda f, this is in the stable range. Okay, so this guy's never in the stable range, really. And this guy sometimes is and sometimes isn't. So let's say that we focus, when we talk about the critical boson theory, sorry, the regular boson theory or the critical fermion theory, I'm always going to mean, for conservativeness, I'm talking about fixed point 2. So this is what I mean. Its theory is defined by deformation away from this fixed point. And then we can discuss a little. Okay. So those theories, at least these regular boson theories, the potential problems go away. And you find this by explicit computation, because you can do all orders explicit computation to all values of lambda in this theory.
Excuse me.
Yes.
I have a question.
Please.
Effective potential is not analytic with respect to phi bar phi.
At 0.
Yeah, at 0, yes.
Yes, exactly. And the reason for that is that when phi bar phi is equal to 0, that happens when you've got the conformal theory. Okay, so this is exactly what you'd expect. What you have is a phase diagram where there is a phase transition between two different phases. And at that phase transition point, you've got new conformal dynamics, new light modes. That is the reason that this was not analytic. Does this answer the question?
Well,
maybe
probably yes, but
yes. Okay, it's the usual thing. New light degrees of freedom lead to non-analyticities. It's the usual thing which you see very explicitly in calculation. Okay, in fact, you can take what I told you about and work out a phase diagram for these theories. You know, I worked out this effective potential, and now you can just take that effective potential and minimize it to see which phase you lie in. And you can work out the phase diagram. It's a more complicated phase diagram than that for the critical boson and regular fermion theory. Okay, it's a more complicated phase diagram because now your phase diagram is just 2 points. There's a mass square and a B4, the coefficient of the phi to the 4 operator. Okay, and you get an intricate phase diagram involving phase transitions, part of some point of which is second order, some part of which is first order, involving phase transitions between this between a Higgsed and an unhiggsed phase. Okay, and this point, this blue line here, is your phi bar phi equals 0. That was the non-analyticity we were talking about. So the story has been worked out in great detail. Okay, excellent. So that's all I wanted to say about stability and beta functions. Yeah, fine. Now let's go back to our list. We've done stability, we've done beta functions. Now what about correlators and duality? Again, I'm going to say this again very briefly. As I explained to you, at MF reg equals 0 and MB, when you switch off all mass terms and work in dimensional regularization, the theories I described are conformal. I've said this for the critical boson and regular fermion theories, similarly for the regular boson and critical fermion theories. Okay. Now, at this conformal point, you know, we can think of these theories not in the language of phases and particles and so on, but in the language of gauge invariant operators and correlation functions. And that's the natural language in which to work for conformal theories. So the first question you can ask is, what is the spectrum of gauge invariant operators in this theory? Okay. And it turns out that the spectrum of gauge invariant operators is incredibly simple. Okay. Turns out that one can argue very simply, using some simple properties of conformal representation theory, that the spectrum of the free theory is not renormalized at leading order and 1 by n. That the first renormalizations in operator dimensions in single sum operators, okay, happens at first subleading order and 1 by n. Okay, so the spectrum of the free theory is just a spectrum of higher spin fields. So for instance, suppose we, it's just a spectrum of operators where the indices mu1 to mu(s) go from 0 to infinity. And the scaling dimension of the spin 0, I'm now talking about the critical boson and regular fermion theory. The other one's a bit different, but minorly different. The scaling dimension of the scalar operator is 2, and the scaling dimension of every other higher spin operator is s plus 1 plus small corrections. Okay. Now these are the spectrum of operators which are of the form 1 phi bar with 1 phi and any number of derivatives sprinkled in between. Or similarly, 1 psi bar and 1 psi, any number of derivatives sprinkled in between. Now, of course, you can have products of these. But the great thing about the large n limit is that correlation functions of these products are factorized. You know, multi-trace operators behave like classical products of single trace operators in the large n limit. So if you know everything about these operators, you know everything about the multi-traces at leading order and large n. So what you've got is a spectrum is sort of like a Fock space of higher spin fields. Okay, so these are the operators in your theory. You've got a very good control over the operator spectrum. Okay. Now in the free theory, these higher spin fields are all conserved fields. This you can easily show by using equations of motion. Turns out that you can argue that in the interacting theory, conservation is violated at subleading orders in 1 by n. Okay, so the del dot j is not 0, but it's jj plus jjj. And Maldacen and Zhibodev in a couple of remarkable papers turned this fact, first worked out these coefficients sort of very precisely, and then used this equation to solve for the 2 and 3 point functions of this theory at leading order in in the large n limit. So it's a remarkable accomplishment, and combining that with the actual explicit Feynman diagram computations, Aharoni and collaborators were able to explicitly compute the 2 and 3 point functions of both the bosonic and the fermionic theory and show that they matched under duality. A little more has been done since then. Some 4 point functions have also been computed. But the net upshot is that using some techniques I will not have the time to review, or even, we know basically all the 2 and 3 point functions of single sum operators in these theories, and some select 4 point functions as well. We know them very precisely in the at leading order of the large n limit, and they all match perfectly under duality. Okay, so correlation functions here in this conformal theory are well understood. There's this sort of interesting algebra, higher spin kind of algebra deformed by a right hand side, and that allows effective computations and allows a non-trivial check of duality. Okay, that's all I wanted to say about correlation functions. As far as I can tell, their main use has been to check duality. Okay, so I give you one example of one very simple example. You remember that the spectrum here had a scalar operator which had dimension 2 on both sides plus small corrections. For instance, with the particular normalization, okay, with a particular normalization, the scalar 2-point function, the normalization such that J0 tilde is sigma for the bosonic theory and JF is psi bar psi by 4 pi. Okay, with a particular, oh, I've written that here. J0 tilde sigma and J0F is psi bar psi by 4 pi psi bar psi by kappa F. Okay, with that normalization, the 2-point functions of these scalar operators have been computed. You get some momentum dependences. I've given you the answer in momentum space. You get some momentum dependences and you get some coefficients. And if you run through the duality map, you find that these exactly agree with each other. So the momentum dependences was really just the fact that it was both were dimension 2. But this agreeing tells you that the two operators map to each other with this normalization. And then that makes the matching of 3-point functions meaningful. And those also match. And I've just told you about the spin 0 operators, but it works for every spin chain. So the evidence from correlation functions for this duality at large n is enormous. Okay, great. So now we believe this duality, right? The duality is correct. Okay. Now I want to use this duality and use large n to understand these theories better. So for the next half an hour, what I'm going to do is to turn to a new computation. So in our list of things that we've run through, we've been through existence and stability, we've been through correlators and duality. Now what I want to do is to try to better understand the Hilbert space of these theories. What beasts are they? And to try to answer the question that we raised about how can it be that phi maps to psi when phi has NB components and psi maps has NF components. Okay, so I want to answer these two questions together. And in order to do that, the computation I'm going to do, I'm going to take you through is the computation of the thermal partition function of these theories. So we're computing the thermal partition function of these theories on S2 times S1. The S1 makes it thermal. Okay. And the computations were done over a series, many papers ranging over years by using Schwinger-Dyson techniques to evaluate the path integral of these theories. For the purpose of this talk, I'm just going to give you the answer that comes out of evaluating that path integral. And then what I'm going to do in great detail for you is to interpret that answer in Hilbert space terms so we get some understanding of what kind of theories we're dealing with. Okay, everything I'm talking about now in the next half an hour or so is based on yet to be published work in collaboration with Abhinav Mishra, Naveen Prabhakar, and Tarun Sharma. Okay, so I'm going to be working in this Stoft large n limit and working with an S2 whose size I also scale to infinity like n. Okay, so the volume of this S2 scales to infinity like n in units of, for instance, the temperature, or in units of the chemical potential, or in units of the mass. Doesn't make a difference because I keep all these other quantities all fixed. So I take the limit n goes to infinity, k goes to infinity, v2 goes to infinity, such that the ratio of any two of these quantities stays fixed, and all other massive quantities stay fixed. In this limit, the path integral of this matter Chern-Simons theory has been worked out. I told you that, you know, v2 goes to infinity in like n. v2 by n is a fixed quantity. And the answer depends not just on lambda and on the massive parameters, but also on v2 times n in an interesting way. So v2 times n is the real parameter, real effective volume of this quantity. Okay. Now I'm going to spend 5 minutes telling you about known results that were obtained using partition path integral methods. The most of the fun we're going to have is trying to interpret that. That I'll go through slowly. But for the results, I will just present them, just give them to you. Turns out that the structure of these partition functions always takes the following form. All the partition functions turn out to be an integral of a unitary matrix with this DUCS measure that we encountered when studying pure Chern-Simons theory. I remind you, DUCS is the usual Weil measure, the measure of the Weil integral formula, the Haar measure, but with a constraint. You integrate only over those unitary matrices such that this condition is obeyed. Okay. Now you integrate it with
we
some
have a question.
Yes.
So one thing I don't understand about equation 19, no? If
Yes.
you integrate from 0 to 2 pi, the rho of alpha, no, it's normalized to 1. So is it okay for all lambda? No, because I get 1 over lambda.
No, it's normalized to 1 by definition. You know, rho is by definition the eigenvalue density function, so that it is, you know, so that the total number of n times the integral of rho measures the total number of eigenvalues. The number of eigenvalues is always n. So the normalization is independent of lambda. Was that your question? Yes.
Yeah, no. So this this equation fixes that lambda is smaller than 1 somehow.
Yes. Yeah. Oh, that. Yes. Please remember that lambda was n over kappa.
Mm-hmm.
Kappa was modulus of kappa was mod k plus mod n.
Ah, okay.
So lambda is always less than.
By construction, I see. Okay, thanks.
By definition. Yes,
Thanks.
otherwise we would have had a contradiction. You're right. Thank you for the question. Other questions or comments?
Yes, sorry, another question. So is use of this measure, it's an assumption or it's derived in some way?
Well, it comes out of the calculation. It comes out of the calculation because we're doing an integral, a path integral over Chern-Simons theory. And when we take into account the flux sectors in that path integral, it comes out. So no, not an assumption, It's derived.
Okay.
Did you have some, was there some discomfort about that? Right. No, it's derived.
May I still the same? Can you physically explain how this constraint appears in the derivation? So what?
So now there are two questions you could be asking. Can you explain technically how it arises, and what is its physical meaning? Its physical meaning we're going to spend the next 25 minutes talking about. But about how it arises technically, let me tell you. You know, when you're computing a Chern-Simons path integral, one of the things you have to do is to sum over all fluxes on S2. If you were doing a Yang-Mills kind of path integral, that would be a highly subdominant thing to do, because each flux carries energy. Okay, that kind of, the fluxes would carry energies like 1 over g squared, and that would be very non-perturbative. Okay. On the other hand, in Chern-Simons theory, fluxes don't carry energy. There's no F squared cost to having that flux. However, having a flux in the Chern-Simons term interplays with the holonomies, because, you know, the Chern-Simons action, roughly speaking, is flux times A0. So if you sum over all fluxes, what you're doing is getting an e to the, and remember there's an I. So it's e to the power I times all integers times A0. Then if you use the formula that e to the power I m alpha, sum over all alpha, is a discretized sort of delta function in alpha, you realize that your holonomies are no longer continuous, but discrete. Okay. Now I forgot to say that, you know, the Chern-Simons term actually came with a kappa outside it. So it was e to the power I kappa flux times A0. And that's what discretizes your holonomies in units of 1 over kappa. And in the large n limit, that gives you this measure. Very much like we saw in the pure Chern-Simons. Does this answer the question?
Yes. Thank you.
Okay. What it means, we're coming to. This is how it came about. But I'm going to tell you what it means. Okay. Excellent. So we've got this integral over the Chern-Simons, this sort of truncated Weil measure of something. Now, what is this something? This something required a lot of computation to get. But in all 4 theories that I've outlined for you, this something has the following structure. It can be obtained by minimizing a relatively simple quantity over some auxiliary variables. Once you do this minimization, this quantity becomes very ugly. But it can be obtained by minimizing a relatively simple quantity over auxiliary variables. I emphasize that this field has developed over years. When we first did this kind of calculation, we didn't realize that we just got the ugly expressions. So only with hindsight that you unintegrate some part of it. Okay. And I'm going to tell you what these simple, nice expressions are for all 4 theories. In the case of the regular fermion theory, this off-shell free energy, this function of things you have to minimize over, auxiliary variables you have to minimize over, is given by this formula. Here, C tilde F and C tilde R are auxiliary variables. These are the ones you have to minimize over. And this formula has a beautiful universal part. That's this thing here. And then something that depends more on details. For instance, depends on the mass of the field. Okay, this is just some, okay. What you're supposed to do is take this object, extremize over, minimize over C tilde and C hat, and that's the thing you put inside this integral here for the regular fermion theory. You see that it's very simple in the end, even though the procedure to get this was not simple. Okay, note this third line is the only part that depends on the eigenvalue density function. Everything else is just depends on basically these auxiliary parameters. Okay, C tilde F has a physical meaning. It is the thermal mass. We will come to that. It's the thermal mass of our system. We'll come to that. In the case of the critical boson theory, the off-shell free energy is given by a sort of similar looking expression, something that's a function of an auxiliary parameter, which will turn out to be the thermal mass, another auxiliary parameter, some stuff, and then some universal stuff. And I'll explain in what sense this is universal in a minute. In the case of the regular fermion theory, the number of auxiliary parameters jumps. It's not 2, but 3. Okay. And for the critical fermion theory, it's given by this sort of increasingly ugly looking first line, but the same last line. Okay. Again, the last line is the only part that depends on the eigenvalue density functions. And in the case of the critical boson theory, this should have been regular boson theory. We've got again some ugly looking first 2 lines, and then the same universal last line. So the universality is this, that when you change the local interactions in your bosonic theory, that affects only these 2 lines. It doesn't affect this line, as you see explicitly from the answer, or from the fact that this line was the same between the critical boson and the regular boson theory, or the same between the regular fermion and the critical fermion theory. Okay, so that was the structure of our partition functions. It was, you're supposed to do this integral.
Question.
Please.
So one of those parameters is thermal mass. You said. What about the other one? Do you have any physical meaning?
Out of the, let me go to the most complicated case. In this case, out of this, CB is the thermal mass and sigma is basically phi bar phi. You know, this parameter whose effective potential we computed sometime ago. Okay, S tilde we've not managed to find a good interpretation for. I would love to know the answer for what this is physically. So for instance, if you turned on a source for sigma, then you're computing the correlation functions of phi bar phi. It's the generating function of correlation functions for phi bar phi. Okay, so there's a very precise map between sigma and phi bar phi. CB is very precisely the thermal mass. It's a pole in the thermal propagators. Sigma tilde, S tilde, I don't know what it means. So out of the 3, I know what 2 means. Sorry. You were saying?
What needed?
Sorry, I didn't hear the question. Could you
the S tilde?
Yes.
Can see.
I'm sorry, your voice is coming in waves. I cannot quite hear you.
Can you show the places where S tilde appears in this equation? I see only 2 places.
Yeah, it appears here and here. That's it.
Yeah.
So S tilde is easy to integrate out. Yeah, so S tilde is easy to integrate out, actually not very uglily. But it's useful to keep it because it turns out that S tilde is a diagnostic of which phase you're in. Okay, so for instance here, one solution to the equation of motion that you get by varying with respect to S tilde is simply S tilde plus sigma b is 0. So S tilde is equal to minus sigma b. That's one solution. That puts you in the unhiggsed phase of the theory. On the other hand, the other solution puts you in the Higgs phase. So you could, if you wanted to, write down 2 different off-shell effective actions, one for the Higgs phase and the other for the unhiggs phase, and then you would have had no S tilde. And then the one in the Higgs phase would look a little ugly because that would be like a quadratic equation solving kind of thing.
Okay, thank you.
Okay, it was a bit ugly, but S tilde really, the only role was to have one single analytic expression for both phases of the theory. If you were willing to give that up, you could give up S tilde and still be reasonably nice. Does this answer your question? Could you hear me first?
Yes, it was, yes.
Okay, so
Fine.
S tilde is a bit of a fake, and maybe it just doesn't have a physical interpretation for the reasons you mentioned. Okay, the other ones are more intimately, they have a clear physical interpretation. Okay, excellent. So let's keep going. So let's summarize. In all four theories, the S2 times S1 partition function is given by an expression of this form, this measure. You minimize over some auxiliary parameters, and then you evaluate this this integrand. Now, in the large n limit, this integral over u with this funny measure can also be done by saddle points. In fact, in various toy models, we explicitly evaluated all the saddle points in a paper we wrote some time ago. Okay, so this integral over u is also a minimization. It's typically a minimization and the integral don't commute with each other. However, in the large n limit, the integral over u is also an extremization. So what you've got is two separate extremizations, and then they commute with each other. So you can rewrite this formula, which recall was only true in the large n limit to start with. It's equally well, you could rewrite it as this object. You take the extremization outside. And then when you do that, the formula here looks much nicer. This is because you remember that there was only one part of this F that had any dependence on U. This was this nice universal third line in all our formulas. And then, so what we can do now is to evaluate this integral over U, and that depends only on this universal part of this F. And then after doing the integral over U, extremize over zeta I. Okay, so this evaluation of this partition function can be broken up into two steps. The first one, which I call step one, which is evaluate this integral over U, and step two, which is then extremize. So in step one for fermions, we are required to evaluate this object. Okay, this integral where I've kept only this nice simple universal part of the off-shell free energy. Note that this thing is a function of C tilde F. So if we first did the extremization, it would become very complicated. But for any given constant C tilde F, this is an extremely simple quantity. Similarly, in step one for bosons, we're required to evaluate this object. Okay. Now, and then once we've evaluated these objects, this IF, which is this integral over U, and IB, this integral over U, what we're supposed to do is to take this IB, let's say for the bosons, decorate it with this other stuff, the complicated part of the off-shell free energy, and then extremize over these quantities. Okay. In our notation, the square bracket with some numbers underneath means take that object and extremize with respect to those objects. Okay. Now, as the questioner asked 2 minutes ago, one of the extremizations is very simple. That's the extremization over this S. That requires you to solve this equation here. Okay. And this equation has two solutions. One, which is sigma B is equal to minus, S tilde is equal to minus sigma B, and the other one, which is a little more complicated. As I explained in my answer, these two equations these two solutions are appropriate for the two different phases of the theory. So if we specialize for a moment to the unhiggsed phase, okay, then here we can just set S tilde is equal to minus sigma B. That is, just drop these two terms in this expression. And if you did that, you get this quantity here. Okay. So what we have to do is to evaluate this IB, then decorate it with, oh, this shouldn't have had an S. Now it's an extremization only with respect to CB and sigma, with this much simpler decoration. Now, I want to show you how this is already a quite familiar formula. It's almost a familiar formula. Suppose we took a non-gauge scalar large N matter theory with a funny potential chosen to match what you see here. And then with the aid of Lagrange multipliers, you can rewrite this path integral as this. What do? Well, I take CB squared, which is some Lagrange multiplier, and I multiply by effectively sigma minus phi bar phi. Okay, and with some normalization. These two, the CB squared integral tells me sigma, what was phi bar phi here can now be replaced by sigma. And so wherever I had a phi bar phi, I have sigmas. And then I have the Lagrange multipliers that set CB equal sigma equals phi bar phi. Okay. And when you go through that, that simple two-line do nothing kind of manipulation takes this path integral and turns it into this path integral, where now you're path integrating not just over phi bar and phi, but also over the field CB square and the field sigma. Now, in general, finite n, this is not buying you. But at large n, it buys you something, because phi bar and phi are n fields, whereas CB squared and sigma are 1. So if you now do the integral over phi bar and phi, which is very easy to do because now phi bar phi has become a free theory. Okay. The effective action that you get for CB squared and sigma can be now evaluated by saddle points. So sigma and CB squared we know are going to be evaluated on those saddle points. If we make the reasonable assumption that CB on their saddle points, CB squared and sigma are just constant fields. This, for the pure ungauged theory, has been checked in many ways to be true. Then that is simply for the ungauged scalar theory, what we're instructed to do is compute the partition function over a free boson theory of variable mass CB square. So that's this trace over the Fock space, free boson theory of mass CB square. Then decorate it with this kind of quantity, and then extremize over CB and sigma. Okay, so it's like a 3-line derivation. I haven't, I maybe missed out a step or two, but it's basically as simple as what I've written here for the ungauged theory to show that the ungauged partition function is given by this kind of an expression. Note that in the gauge theory, we have an exactly same kind of expression, except that the role of the Hilbert space over a free boson theory of mass CB, its role is played by this IB. Recall IB was this quantity. So what's happening here is that the theory is behaving like it's an ungauged theory, except that this partition function over the Hilbert space of a free boson, of a free Hilbert space, is being replaced by the partition function by this IB. So in order to understand what this RB, this partition function here is, really the crucial element is to understand IB. Okay, so that's what I've said in equations here. The two expressions are sort of structurally the same, except with one replacement, that the trace over the Fock space, the partition function of the free boson theory, is replaced by this IB. Now, the fact that this Fock space partition function here appeared was representing something physical. The physical thing was that a theory, an ungauged large N matter theory, its Hilbert space is essentially a Fock space with forward scattering renormalizations of energies. The forward scattering renormalizations of energies are the decoration and the extremization. Decoration and extremization. So what we are getting in our gauge theory is whatever replaces free bosons, and then with forward scattering renormalizations of energies. Okay, so what we need to know is what is it that replaces the free bosons? Okay, so now we turn our attention to that. What the hell is this IB of CB? What is it a partition function over? What space?
But sorry, Shiraz, can one explicitly check this IB function of Fock space, because it has a special
Sorry, can one check IB what?
Can one explicitly check that IB is the partition function of a Fock space?
It's not the partition function of a Fock space. Okay. So in the ungauged matter theory, what was the partition function of a Fock space is replaced by IB. And IB is whatever it is. It's not the partition function over a Fock space. We're soon going to find what it is.
Oh, okay. Thanks.
Okay. So I'm going to work it out first for IF because it's a bit simpler, and then we'll turn to IB. So IF was this quantity. Now, IF is not going to be the partition of a function over a Fock space, but note that this quantity, this ZF NSU, which was this quantity, that is simply the partition function over a free fermion Fock space, where the fermion has UNF flavor symmetry, and you twist that Fock, you twist the partition function with unitary matrix and this UNF flavor symmetry. This, just by direct evaluation, is true. This is just that determinant. Okay? So this IF is simply this quantity. It's the integral over DUCS, this almost Haar measure, of the trace over a Fock space of a twisted partition function, twisted by this, by U, and then you integrate over all U's with this funny Chern-Simons measure. Is this clear? Great. Now, IB is something sort of similar. We have an integral over this Chern-Simons measure with this quantity, except that the thing that appears inside this trace is a little more funny. There's this quantity, this twisted trace of over the Hilbert space, and then there is this funny stuff here involving a theta function and mod mu minus c. Okay. Clearly, the bosons are more complicated than the fermions. First deal with fermions, then we move to the bosons. So now we want to first give an interpretation of this quantity IF. Before turning to interpreting it precisely, let me recall that there is a similar quantity that has a very simple and very familiar interpretation. Suppose du wasn't this funny measure, okay, but it was just the usual Haar measure. Then what is this quantity? Well, then either you're familiar with this or a moment's reflection will convince you that this quantity is simply the trace over a Fock space projected down to UNF singlets. You know, you twist over U and then you integrate over U. That integral implements the projection down to singlets of classical UNF theory. Okay. So were we to replace DUCS by the usual Haar measure, then this quantity IF would have been not a Fock space, but the projection of a Fock space down to UNF singlets. Okay. What is it? Now the question we're going to ask is, what is the actual IF, not this toy model for IF? But the analysis that we gave at the beginning of this talk has given us the answer. Because you remember that, for instance, in the case of the type 1 theory, this sum over all solutions of those funny equations that I wrote down to you before, goes in the large n limit to this DUCNS equations. And the sum over these solutions was the projector onto conformal blocks, or what you can think of as Wess-Zumino-Witten singlets. Or there's an equivalent mathematical way of saying it that I will make no use of because it may not be so familiar, but it's also equivalent to the projection onto the singlets of not the classical group SUN, but the Q-deformed quantum group SUN, where Q is e to the power 2 pi I by kappa. Okay. So this quantity here, this IF, actually we know what the answer is. It is the partition function over the Fock space of fermions projected onto the space of SUN, where SUNF level K Wess-Zumino-Witten singlets. Equivalently, space of conformal blocks, equivalently the space of quantum SUNF singlets. Q-deformed quantum SUNF singlets. Okay? So now we have our interpretation for what this IF is. It's not a Fock space, but it's related to it. It's the projection of this Fock space down to the space of Wess-Zumino-Witten singlets. Is this clear? Any questions or comments about it?
Yes. So, I mean, does the Fock space of the fermion decomposes into just say integrable representations as opposed to generic representations? Yes,
excellent question. Excellent question. Okay, and we're going to come. That question will really hit us when we talk about the bosons. But for the Fock space of the fermions, the answer is yes. You see, because at the naivest level, you might think that each mode is simply a fundamental because our matter was fundamentals. Now, that's not quite correct, right? That's not quite correct because you have to also impose Fermi statistics. So the representations that appear when you impose Fermi statistics are antisymmetric representations. But those antisymmetric representations are just antisymmetric up to n. Another way of saying it is that each single particle state can be occupied once or twice or thrice up to nf times. And when it's occupied any number of times, the representation that appears is just one column whose length is no more than n. Those are all integrable, right? Because you never have large rows, because Fermi statistics makes everything antisymmetric. So in the Fock space of the fermion, and then of course, after that, you get what you get. In the fusion of two of these, you may naively think you're getting some non-integrable representations. But that the fusion rules deal with, the Wessel-Witten fusion rules deal with. The fusion rules close on integrable representation. It's what you put in. And the things that you put in are only antisymmetric columns, which are all integrable. Is this clear?
Thanks.
Okay. Yeah. So, wow. So fine. So now this is great. We've got a clear interpretation of IF for the fermions. But now what's the deal with the bosons? You remember the bosons were a little more complicated, right? And you might have first think, where was I? Yeah, here's this funny complicated stuff here is coming from the bosons. You might first think that if the fermions work, great, but then the bosons won't work because there's this additional stuff. But in fact, Francesco has basically intuited the answer to that question. Okay, the difference is the following. With the bosons, when you start occupying particle states, you would get both integrable as well as non-integrable representations, because you would get representations now with symmetric guys. And if you have, there's no limit to the number of bosons you could put into one state. And when that number of bosons exceeds k, your representation would be non-integral. So we are going to interpret this as follows. Every time we encounter a non-integrable representation, we're going to throw it away. And the reason we throw it away is that Geppner and Witten showed that that conformal blocks involving a bunch of integrable representations and one or more non-integral representations always vanish. So if we project to the space of Wessel-Witten singlets or conformal blocks, we're going to interpret any appearance of a non-integrable representation as 0. Okay, and then we're going to check whether with that interpretation we get the formula that we got from path integrals. Okay, so now let me say this more explicitly. So explicitly, we take this twisted trace of this partition function here over the Hilbert space, Fock space of bosons. Okay, that is this quantity here, so, a Bose factor for every single particle state. A runs over every single particle state. And then we take each of these Bose factors, these are twisted, and we expand them in a character expansion. N is effectively the number of particles occupied in this state. When N goes past KB, we're encountering these non-integrable representations that Francesco was worried about. Okay? So if we were to implement just this twisted trace, we wouldn't be doing the right thing, because we are supposed to throw away the non-integrable representations. So instead of this formula, what we should be doing is taking this formula where this line KB implies expand this quantity only up to order KB. Okay, that would give you the true truncation to Wessel-Witten singlets. Okay, now by some manipulations that I'm running, I don't have the time to, it's trivial manipulations. This thing can be manipulated to an unrestricted quantity here at the expense of putting something in the numerator to kill off all the terms you didn't want. Okay, and so when you take the log of this quantity, you get the log of what you would have had you had no restriction, plus the log of something else. This y here is e to the power minus beta times Ea minus mu, where Ea is the energy of the state and mu is the chemical potential. Now you see, this quantity is what it is, but in the large n limit, kappa goes to infinity. So if y is less than 1, this is 1 minus y to some very large power, and that's basically 1. And so you get log of 1, which is 0. So this just goes away. On the other hand, if y is greater than 1, this quantity becomes very large. In that limit, you can forget about the 1. So this is just log of minus y to the power kappa. And that is up to some I factor because of the minus, which is subleading in large n. You just get kappa times log of, oh, this w should have been a y, log of y. But this only happens when y is greater than 1. So you get it with a theta function, theta of y minus 1. But remember, y was e to the power minus beta ea minus mu. And y is greater than 1 when mu is greater than ea. So this theta function is the same as a mu minus ea. Now you get one such factor for every single particle state. Now some single particle states have energies greater than mu, and they don't contribute because this theta function is 0. But for those that have energies less than mu, you get a factor for each such state, and when you do the integral over all such states, and work it out, you find exactly, I mean, including all numbers, exactly this quantity here. So you see that the appearance of this quantity in these large n partition functions that we computed before was actually just telling you that the bosons are different because when you restrict to the space of Westermino-Witten singlets or quantum group singlets, you have to first truncate to integrable representations, as Francesco intuited. Okay, so both the bosonic and the fermionic formula both have the same interpretation. They're the partition function over Fock space restricted to Westermino-Witten singlets or quantum group singlets, appropriately understood, including this throwing away of non-integrable representations. Okay, so now we understand what's going on. Our final Hilbert space, our final Hilbert space is simply you replace Westermino with we replace the Fock space by this truncation of Fock space to the space of Westermino-Witten singlets, and then you allow for forward scattering renormalizations. That's the other dressing one. That's not novel. That's been understood for 30 years. The new thing that's not been that's new is this truncation to the quantum group singlets. Okay, so just like ordinary ungauged matter Chern-Simons theories should be thought of as Fock spaces with forward scattering renormalizations. These theories should be thought of as Fock spaces truncated to the quantum group singlet sector with forward scattering renormalizations. Okay, now in going through this, we've learned something important here. In large n matter Chern-Simons theories, we've just learned, because of this truncation to the integrable sector, no single particle bosonic state can be occupied more than kb times. Okay, that's part of the condition that we're truncating to the Westermino sector. That's what that theta function was telling us. And this we call the bosonic exclusion principle. This is the direct level rank dual of a more obvious result for fermionic theories, namely that no single particle fermionic state can be occupied more than nf times. Okay. Now, this has a very interesting dynamical consequence. Recall that a theory of free bosons is unstable, just as nonsensical when the chemical potential is taken to be greater than the mass. It's nonsensical because there are some states, those whose energies are smaller than the chemical potential, that have a Bose enhancement rather than a Bose suppression, a Boltzmann enhancement rather than Boltzmann suppression factor, and the partition function over those states is just infinity. This is the runaway instability of Bose condensation in a free boson theory. On the other hand, in our theory now, this instability is cured because that instability is just saturated out. All states that have this Bose enhancement will be occupied, okay, at most kb times. So there's no instability. So this gives a very beautiful way in which this Chern-Simons theory cures the instability of Bose condensation in these theories. And in fact, it cures it in a way that makes these Bose condensates very similar to Fermi seas, because everything is completely filled up to a certain momentum. And indeed, under Bose-Fermi duality, these Bose condensates are dual to Fermi seas. This could have been, the way it works is because of this bosonic exclusion principle. Okay, so let's recap. The partition function of large N matter Chern-Simons theories is given by an expression of the same form as their ungauged counterparts, with the replacement of the Fock space partition function to its Wessel-Witten singlet projected counterpart. It's clear that the Wessel-Witten singlet constraint has a huge effect on the partition function. You know, when the volume is large enough. When the volume is small, because it's a singlet condition. But one might naively expect that this Wessel-Witten singlet condition doesn't affect the partition function very much when the volume is taken very large. You know, that is what was true of the classical Gauss law singlet condition. That's just n square conditions on many, many, many photons if you take very large volume. And so it becomes a negligible effect on the partition function. However, that turns out not to be true for the Wessel-Witten constraint. We've already seen this in the case of Bose condensation, for instance. But you can see it more generally. Let me give you 2 minutes on how that works, and then we'll quickly go on to the next topic. And the 2 minutes on how that works goes as follows. Suppose we took this program of taking the Fock space partition function and constraining to the Wessel-Witten singlet sector. What one is supposed to do is to do a sum over, you know, different solutions of some equation like this. Now, in the infinite volume limit, one can show that in the summation, one term in this summation, we've got a finite number of terms. One term in the summation dominates over all of this. Okay? And so that term is the term where WIs for all type 1, type 2 SUN theory take the following form. Take this very simple configuration of eigenvalues. This is the configuration of eigenvalues that is as close as it can be to identity, subject to the constraint that no two eigenvalues are allowed to be equal. Okay? So this one term in that sum dominates over everything, all others. And that means that the this IB partition function is a product over partition functions, one for each state. It was always a sum over products, but now it's not a sum over product, just a product over partition function, one for each state. Which means that up to some unimportant normalization constant, the partition function is a product of partition functions, one for each single particle state. Now, this sounds very strange, because normally, if you've got a partition function that's a product over single partition functions, it means that what's happening in one single particle state is not affecting what's happening in the other single particle state. That's why it's a product. That's why it's non-interference. It's a free theory. However, that's not what's going on here. It's not that there is an independent Hilbert space per single particle partition state. As you can see from the fact that if you take these ZABs, these single particle partition functions, evaluated on this particular holonomy and expand it in an e to the power minus beta expansion, the coefficients are not integers. Indeed, what you find is that, for instance, when you take the bosonic theory, you get this ZAB is quantity of this form, where this quantity is the character of the nth symmetric box representation of SUN evaluated on this very special eigenvalue configuration. And when you work that out, this is what's called the quantum dimension. This quantity is what's called the quantum dimension of the n box representation. And when you work that out, you get very nice and beautiful formulas for all these things. Q-deformed versions of what you would have got ignoring in ordinary Bose statistics. Okay. Now, I told you about this puzzle about how it could be that you've got a partition function that's a product of single particle partition functions in a system where the difference between the free theory and this theory is coming because there's some sort of global constraint. And the way that works is due to a particular feature of Wessel-Witten representation theory, which I've outlined in these slides, but I have no time to go over. We think we understand this explanation, but I refer you to my slides if you want to find. You want to look at it. I'll just end this part of it by saying that, look, in the end, what we've got in this large volume limit is the partition functions, a product over partition functions, one for each single particle state. So the theory, for many purposes, behaves like it's a free theory, but a free theory with the new statistics, because each particle, the occupation number statistics is new. It's a Q-deformed version of the old statistics of either Boson or Fermi. And you get new deformations of very familiar formulae. For instance, the formula for the number of particles in any given bosonic state, which is familiar to all of us from our undergraduate studies, it gets replaced by a Q-deformed version of that here, and so on. There are many things to say about this, but let me move on. I'll just take 2 minutes to say one last thing, and then I'll stop. The last thing I wanted to say is that now we're on the next topic.
Sorry, before you go to the next topic, did you compare this statistics with so-called exclusion statistics? There is this known statistics in one dimension when you add particles that it takes more or less than one state out of Hilbert space, and there were formulas written for occupation numbers.
Are these what people call parafermions?
It's called exclusion statistics, or
no? Then I've not. I wasn't aware of this, and I haven't compared.
Okay.
Thank you. Okay. Yes. Okay. Now the last thing I want to tell you about is scattering in these theories. Okay. There's a quick qualitative lesson I want to give you, and then I'll stop. We'll forget about the magnetic field. It's in my slides. Okay. See, the gauge non-invariant 2-point functions of phi with phi bar, or the W boson with itself, or psi with psi bar, have been computed. That's actually the first step in many of the computations I told you about before. This is gauge non-invariant, but it feeds into as a building block into a gauge invariant answer when you compute for its free energy. But this gauge non-invariant partition function has correlation function has one gauge invariant piece of data, and that is in the location of its poles. So just like the 2-point function of an electron operator is not gauge invariant, but where its pole is gives you the correct electron mass. In the same way, the gauge, the full correlation function here is not gauge invariant, but the location of its pole is. And one of the tests of duality is that the locations of the poles match across duality. Okay, so the poles for phi bar phi and W bar W in the appropriate phases match the poles for psi bar psi. So this is telling us that, we have these excitations, and if we were on R2, we can take these excitations and scatter them using the LSZ formula. Now, if you did that, and we have done it, you might at first have the following worry. How can it be that the S matrix of two fermions matches the S matrix of two bosons? Because, one should obey Pauli statistics or Dirac, whatever, fermionic statistics, while the other should obey Bose statistics. So if you have two diagrams, you should add the two of them with a plus sign, for instance, for bosons, or with a minus sign for fermions. So even if diagram by diagram things agree, how could it possibly be that the whole thing agrees? This is something that worried me a lot at some point. But then you just do the calculation and you see how beautifully it works. Suppose you scatter two fermions. Fermions, so fundamental, two fundamentals to go to two fundamentals. Okay, suppose you're doing that scattering process. Now, that scattering process could happen in a channel where the two fundamentals are coupled to the symmetric gauge representation or to the antisymmetric gauge representation. And when you do the calculation, you find that the bosonic S matrix in the symmetric channel agrees with the fermionic S matrix in the antisymmetric channel, and vice versa. And once you realize that, everything falls into place. You see, basically what's going on here is the following. You've got a state that has to obey, a multi-particle state that has to obey, let's say, Fermi statistics. But it obeys Fermi statistics under interchange of all its quantum numbers. Now let's separate out the physical quantum numbers, which are like momenta, from the gauge quantum numbers, which in the end in some gauge invariant state will be invisible. The Fermi statistics is obeyed by the interchange of all quantum numbers, including these gauge guys. Okay. Now, if that maps to the way I've told you about, such that antisymmetry in gauge indices maps to symmetry in gauge indices on the bosonic side, then anti-symmetry under the physical let's say symmetry under the exchange of the physical quantum numbers maps to anti-symmetry under the exchange of the physical quantum numbers on the other side. So under exchange of I said it wrong. Anti-symmetry of the whole wave function and symmetry of the whole wave function imply equal statistics for the physical quantum numbers, because the difference in the statistics is taken care of by these invisible gauge quantum numbers. Okay, so this is the way duality is working. The difference in statistics is compensated for by these hidden quantum numbers, which are just gauge indices. Notice that this map, that symmetry maps to anti-symmetric, is the same as the map for Wilson lines under level rank duality, as we reviewed at the beginning of the talk. So it's something we should have expected if we were foresighted enough. This gives you another insight into how these dualities are working in these theories. We saw earlier that spins matched. We're now seeing the statistics also matched in these theories. Okay, that statistics doesn't bar Bose-Fermi duality, even though you might at first think that it should. One thing to put out of the way, you know, some people might have thought that the way it's going to work is that, you know, what you're going to scatter is neither bosons nor fermions, but anions, and you get the same anions on the two sides. And indeed, that's the explanation of how things work in another channel, when you scatter fundamental with anti-fundamental. But when you look at the details, when you scatter two fundamentals, that's not the explanation of how things work. The anionic phase in the large N limit is of order 1 over n and negligible for dynamics in that channel. Okay, so it's not that that anions are the same on both sides. It's that the hidden quantum numbers compensate for statistics. Okay, then there's some connection to supersymmetry, which I'll skip. There's and there's the connection. There's the B field, which I'll skip.
A question.
And we just move to questions. Yes. So this is the end of my talk. I'm sorry I couldn't cover everything. I tried to cover it.
So I have a question.
Yes.
Maybe, okay. Can I think of your model at large N as taking the free particles, free bosons and fermions, and putting them at the end points of the Wilson lines of the Chern-Simons theory? So when I have like K bosons, after a while, I cannot get the integral representations from the Wilson lines. So I cannot put more than a certain number of them. And with the fermions, it's okay because they are antisymmetric. So it's like you're describing the particles on which the Wilson lines can end in some way. Does that make sense?
Yeah. In some sense. So, you know, the language I think in is the following. And maybe there's some way in which what you say is equivalent, but let me tell you how I think about it. Let's go to the non-relativistic limit, okay, where everything I said works for arbitrary mass. So we could go to some temperature that is small compared to mass, and then everything becomes some non-relativistic limit. So a special limit of everything I said is a non-relativistic theory. In this non-relativistic theory, we know exactly how things work. Okay, how things work. What we have is we're describing our states with a Schrodinger equation. And the Schrodinger equation is a free Schrodinger equation for a particle of a particular spin, which you can easily write down on a two-dimensional sphere, for instance. With the one caveat that when one particle goes around the other, it picks up a phase. That phase is not a number, it's an operator, right? Because it depends on the indices of this quantity. So one can write down, you know, it's like each particle traps magnetic field because of the Chern-Simons equation of motion. And that gives you an Arnaud-Bohm phase, except that it's an operator, not a number. And then the whole thing then has to match up so that when you go around, if you go around, the phases should be such that when you go around nothing, it's single valued. Okay, so this Schrodinger equation one can set up and in simple cases even solve. And this is how I think of the problem. It's this non-abelian multi-particle Arnaud-Bohm kind of problem, which in this large N limit remarkably simplifies. Perhaps perhaps there's some language in which we can discuss it in your what you're saying, but I'm not 100% sure.
Oh, okay, thanks.
I have a question on the partition function on S2 cross S1.
Yes.
So the theory, bosonic and fermionic theory are related by duality, right?
Yes.
So can you say that the formula that you got for the partition function in the large volume limit, they match?
Yes, yes. I didn't say that, but they match on the nose. They match on the nose. In fact, the fact that IF and IB match each other, if CB equals CF, is sort of obvious. It follows from the fact that Wilson loop expectation values in Chern-Simons theories match each other on the nose under level rank duality. Okay, so that even without checking, one can prove. Do you understand what I mean? Because you see, all that IF. So let me say that. Let me say that a little more detail. I'm sorry I didn't say this. This was an important thing I should have said. Yes, thank you. You see, all that IF is a trace over a fermionic Hilbert space weighted with respect to, projected down to SUN Wessel-Minowitten singlets. And on the other side, you've got a bosonic Hilbert space projected down to its Wessel-Minowitten singlets. Now, that projection, so what you can do is to just work out what that projection means. Let's just expand the Hilbert space into all possible occupation numbers, and then you get a particular conformal block number depending on the occupation number of each state. Okay, so if you have 5 particles occupied in one state, that will be a representation with the five symmetric boxes on the bosonic side. And if you've got 3 particles occupied in one fermionic state, that would be 3 antisymmetric boxes on the fermionic side. So, and then the number of this sum over eigenvalues with those character insertions can be proved in pure Chern-Simons theory to match with each other when you interchange purely symmetric with purely antisymmetric. So those numbers are just the same. And then the 2 partition functions, then you can just show that they're the same for IB and IF. And then the whole partition function then will agree if this off-shell part, the dressing part, this forward scattering part happens to agree. And that you can also check by direct large N computation is the case. So these 2 things agree in a very beautifully structural way. I'm not sure I was completely clear, but does that answer your question?
So my question is, was the bosonic and fermionic partition function, they are equal in the large volume limit, which is a semi-classical limit, if you want, or they agree also for any value of the radius of the
radius. Okay, excellent. So when we look at the large volume limit, there are 2 things you can mean. Okay. The first is take V to be of order n, but make it alpha times n. The partition function is a non-trivial function of this quantity alpha, and it agrees for every value of alpha. Okay, so V being order n is not, not all order n's are the same. If you take V to be alpha times n in, let's say, units of the temperature, the answer depends on alpha and it agrees for all values of alpha. Now you might ask, okay, what about V, which is order 1, not order n at all? Okay. Now, in this new paper that we're writing, we're going to conjecture that, you see, in the old partition function computation methods, our techniques were only powerful enough to give us the answer when V was alpha times n for any value of n. But that answer takes this form. That answer takes this form here. Sorry. That answer takes this form here. Where was I? Sorry. Yeah. that answer takes this, let's say for the bosons, that answer takes this form here. And this form is well defined for any value of the volume. So though we don't have a direct derivation of it, we're going to propose in our new paper that this formula is correct for all values of the volume. Okay, not necessarily large. And if you believe this conjecture, then duality, match under duality is true at all values of the volume. I want to emphasize that we've not directly computed. We've only, that this matches what we've directly computed when the volume is of order alpha times n. But it's such a natural and beautiful formula for all values of volume. We just believe that it must be true. But if you make that conjecture, then duality works.
Okay.
Does this answer your question?
Yes, thank you.
Okay, excellent.
I have another
please,
comment.
please.
In principle, on the sphere, you should also include solitonic solutions. So the partition function could be, calculation of partition function could be extended by including solitonic sector in the space. Okay, that would affect the numerator of this Boltzmann sum. So somehow it's a subleading effect for large R, but in principle, with such a geometry, you can also include the solitonic sectors. Do you agree?
These are solitons in the matter?
No, in the gauge field.
Those have been taken into account.
Already taken into account?
Yes, these are like the flux sectors.
Flux sector, yes.
Yes, and they were taken into account in computing.
Okay, thank you.
Yes.
Do we have more questions? Yes, we have another one.
I had just curiosity about the amplitudes, the scattering amplitudes.
Yes.
So is it clear how to define them, let's say, even beyond perturbation theory, or because like in principle, we have these charged particles, so I guess LSZ is a bit subtle, right?
Wonderful question. Wonderful question. I feel that the correct way to define this is by taking into account the new light states we're going to have at infinity. So for instance, let's take a toy model. Suppose we were regulating space at some radius r. Okay, so that our space wasn't, spatial sections weren't going out to infinity, so space was a disk, and there was a boundary of the disk. Then we know that at the boundary of that disk, we have the modes of chiral Westermino-Witten theory living. So the full Hilbert space is not just given by the matter theory, matter excitation. That's what we are sort of assuming here. There's also the degrees of freedom on the boundary of that disk. And when we do the scattering, we should be keeping track of what happens to those modes. And I believe that this is the heart of all the funny things we're seeing. So I very briefly alluded to the fact that when you compute these S matrices, the usual rules of crossing symmetry get modified. Okay, I believe that these massless modes at the boundary are the heart of what's happening, but I haven't, and there are some indications that's true, but I haven't completely satisfactorily cleared this up. And a computational check of this is the following. Just by doing a computational goal is the following. Just by doing actual computations in the large N limit, we've computed the modification of the crossing symmetry rules. So in some sense, we know what the answer should be at large. And we've checked that these answers are universal. You do it for fermions, you get the same answer. You do it for bosons, you get the same answer. You do it for a theory with one boson, one fermion, you get the same answer, and so on. Supersymmetric theory, you get the same answer. So there's independent of what the details are, you get some new modified crossing symmetry rules. But we only know the answer at large N because we could do the calculation. Now, there are some things that one will never be able to calculate, right? At n equals 3 and k equals 4, you'll never be able to calculate, presumably, analytically, the S matrix of these theories, the final S matrix formula. But some things one should know analytically, and crossing rules, not what each S matrix is, but what the relationship is when you cross. That's the kind of thing that one should know. So a computational goal here, sharp goal to test your understanding would be, can you find the right answer, the correct answer for the modified crossing symmetry rules at finite n and k? I think this should be something if one's clever enough, one should be able to deduce. And I think it's very interesting because it's a deformation of one of the fundamental structures of physics, namely crossing symmetry of an S matrix. Okay, and once you understand that, I feel it'll have many applications.
Finite n, large k, or
I meant finite n and finite k. Finite n, large k, of course, one could make some progress by perturbation theory. But I think that this is the kind of thing where you should be able to understand it without having to do too many computations. But I mean, I can't promise anything until I do it.
okay, thanks.
More questions? Okay, so if not, let's thank Shiraz for this beautiful review.
Okay, I'm so sorry I couldn't go through everything I meant to say. If anyone's interested, the slides have more material than what I was able to talk about.
Yes,
Okay, thank you very much, Francesco, for the invitation, and thank you for all the discussion and comments.
yeah, thank you. Thank you very much. Goodbye. Nice evening.
Bye.